All right, so today we are looking at what we call reciprocal functions. So in mathematics, when we talk about reciprocal, we mean 1 over something. All right, 1 over whatever it might be. Now, here for circular functions, the reciprocal would be 1 over sine, 1 over cos, 1 over tan. Now, if we did things like, say, if we got a to the minus 1, for example, would be 1 over a. But with trigonometry, the way we write things when, if we squared sine and also then inverses and stuff like that, it could get a little bit confusing as to what they actually mean. So for circular functions, the reciprocal functions, these ones here, 1 over sine, 1 over cos, 1 over tan, they're given some special names. All right, so we don't use this kind of index notation for our reciprocal circular functions. We give them some special names. And so here's our special names. So one on cos is what's called secant. One on sine is what we call cosecant. And one on tan is called cotangent. Now, cot, of course, because tan is sine on cos, cot can also be expressed as cos on sine. All right, so for reciprocal circular functions, these three names are used. If you see some -1 power or that kind of stuff, that means something else for circular functions, which we haven't got to yet. But when you do, so that's, and you see it, you need to think, okay, it's not related to this stuff. All right, hope I haven't confused anybody by saying that. So for circular functions, reciprocal functions are 1 over, and that we use these names. That's all we use, is these names, unless we physically write the 1 over sign, but normally it would be written as cosec. All right, so we can find values of things. So here we go. Find the exact value of sec 2 pi on 3. So sec 2 pi on 3. So sec relates to cos. All right, and so sec of 2 pi on 3 is 1 over cos of 2 pi on 3. Now, we can figure out cos of 2 pi on 3, as we can come to our graph here. There's our circle, 2 pi on 3 is over there. This angle, our reference angle, is pi on 3. And so we've got all the information we know. So it's second quadrant. And in second quadrant, cos is negative. Our reference angle, already done that. And that's pi on 3. Squeeze that in. Should have left myself a little bit more space anyway, not to worry. All right, so I'm referring here to just the cos part. So cos of 2 pi on 3 then, it's negative, and it's related to the cos of pi on 3. And when you look at your thing, you find that the cos of pi on 3 is a half. So sec of 2 pi on 3 then, which is 1 over the cos of pi on 3, so that's 1 over negative a half. If we're if we're dividing by a fraction, we turn it upside down and multiply. So we've got 1 times negative 2 on 1, which is negative 2. So the sec of 2 pi and 3 is negative 2. All right. So that's how we can use our exact values from our sine, cos, and tan in that way to help us find sec, cosec, cot. All right, we can also solve equations. So find the values of x between 0 and 2 pi, where the cot of x is negative 1. All right, so negative, cot is related to tan. So cot relates to tan. And so it's negative, and tan is negative. So we're in the second and fourth quadrants. All right, so let's have a look over here. Second and fourth quadrants. Okay, so our reference angle is 1 here. So our reference angle is relating to tan of 1, because I've used the minus to find the quadrants, knowing the cot is related to tan. So I want to find the sine of tan minus 1, so inverse tan. All right. And that's pi 4. All right, so you can see what I mentioned was waffling on before about why we don't use index form for our reciprocal functions, because inverse tan means something else, and so we don't want to get confused. Anyway, I digress. All right, so pi on 4. So what do we got then? All right, so we know that cot is equal to 1 on tan. All right, and we already know that, already talked about that. We've already used that. That's why we've done all of this stuff, because of that. I actually don't need to use that anymore, because I know my reference angle there, this here is pi on 4, and these are the angles that I am looking for. So that one around to there, and that's pi minus pi on 4. And then the other one, we can go all the way around to there, which is 2 pi minus pi on 4. All right, neaten that up. 4 minus 1 is 3. 2 4s are 8 minus 1, 7. And there's our answers. All right. Yep, I think that's about all that we can need to talk about there. Okay, Pythagorean identity. Okay, our old friend Pythagoras, remember? A squared plus b squared equals c squared. Well, we can apply that to here, as it says. So we've got hypotenuse, we've got 2 sides. Just so happens that on these particular sides, the a and the b are sine and cos, and the c is 1. So if we do that, we can say that sine squared plus cos squared is equal to 1 squared, which of course is just 1. It's a bit icky, that one. Let's redo that. There, theta. All right. Now, we can, so that's the Pythagorean identity. So we can now rearrange that Pythagorean identity to get some other stuff. So if we then divide everything by sine squared, or cos squared. Let's go cos squared first of all. Then what we get is sine squared over cos squared plus cos squared over cos squared, and then 1 over cos squared. Now, sine on cos is tan, so this is just tan squared. Something over itself, of course, is 1. And 1 on cos is sec, so this is sec squared. So there's another variation of our Pythagorean. Now, of course, I've just divided everything by cos squared there. I could also divide everything by sine squared. And when I do that, I get sine squared over sine squared plus cos squared over sine squared equaling 1 over sine squared. All right, sine on sine, it's 1. Got me squared there. Cos on sine, of course, is cot. So that's cot squared. And 1 on sine is cosec. So that's cosec squared. So there's another variation on the Pythagorean. Okay, so we can, oh, excuse me. We can use those things to help us solve some stuff. So Pythagorean identity is this one, and some couple of variations on the Pythagorean identity are these two. All right, so here we go. Example: if sine theta is 3/5 and theta is between pi on 2 and pi, find the cos and the tan values. All right, there's a couple of ways we can do this, but anyway, this pi on 2 to pi is the second quad. So we'll use that later because in the second quad, cos is negative and tan is also negative. All right, so if we look at the Pythagorean, sine squared theta plus cos squared theta is equal to 1. And we know what sine is, so that's 3/5. So 3/5 squared plus cos squared equals 1. Now 3 3s are 9 and 5 5s are 25. Then we need to take 9 25ths. Now 1 of course is 25 25ths. Minus 9 is 16 25ths. And then we're going to square root to get cos. So we're after cos theta, and when we square root, it's plus or minus 4/5. Now, second quad, cos is negative. Already said that. So the cos value that we're looking for is the negative 4/5. All right, so that's that. And then tan, of course, is sine over cos. And of course now we have both of those values. 3/5 was the sine value. -4/5 is the cos value. Dividing by a fraction, turn it upside down and multiply. And so the tan value is -3/4. Alright, so there's how we would use the Pythagorean to assist us there. Alright, next one. Alright, so next one, cosec x is 7/4. Find cos x. Okay, so let's have a look. What can we get here? What can we get? Cosec x is 7/4. So cosec is 1 on sine. And that equals 7/4. So I'm going to use these two bits. And what I'm going to do is I'm going to flip it. And because then when I flip it, I get that sine x is 4/7. And we're after cos x. So we can again use our Pythagorean. Sine squared x. Let me just change in the way I'm writing things. Let's put that 2 up there a bit more. Sine squared x plus cos squared x is equal to 1. So 4/7 squared equals plus, not equals, plus cos squared is 1. So I'm going to do 2 steps at once. I'm going to move it and square it. So 16 on 49. So 1, of course, is 49 49ths. And 49 minus 16 is 33. So cos squared x is 33 on 49. And then to get cos x, because that's what we're asked for, we square root both sides, plus or minus. The square root of 33 is essentially that, and there's no square numbers that go in, so we can't simplify that. And of course the square root of 49 is 7. Now this time, because we weren't given a domain for x, we don't know which one of those we want, so we give them both as examples, both as answers. So it could be either of that depending on what quadrant, and we're not told what quadrant this x is in. All that we're told is the cosec of it is 7/4. So again, that's related to sine. So this could be a first or a second quadrant angle. We don't have the information to tell which it is. So therefore we keep both the plus and the minus. All right, now the next bit, proofs. This is the fun part. All right, so with proofs are interesting mathematical things. So key, let's go, get rid of that, thank you, is that we're asked to prove that that is equal to that. So with proofs, what you have to do is you have to work with one side at a time only. All right, you can't go switching things. When things are equal, and in the past when we've rearranged stuff to find x-intercepts and the like, we've split things both sides because we know those things are equal, so we can move them around. Here we don't know that they're equal, even though it's suggesting that they are. We've got to prove that they're equal. So what you do is you work with one side at a time only. And often, as in the case with this one here, you only need to worry about working with one side. All right, which side do you choose? Well, kind of rule of thumb that I use is which one's got more stuff that I can play around with. And so for me, when I look at this, this has got more stuff for me to play around with because we've got a couple of fractions. They are fractions. Yes, they're not numbers, but they're still fractions. And so I can add fractions together, and I add fractions together by getting the common denominator. All right, so there's a whole bunch of stuff that's possible for me to do here. This one here, there's not much I can do. All I can do is replace cosec. So there's not a lot there. All right, so the way we set out proofs is also a little bit, technical mathematical stuff. And because we're in specialist mathematics, we need to learn about our technical mathematical stuff. So what we do is we say, right, where am I starting? I'm going to start with the left-hand side. Left-hand side. And the left-hand side is equal to 1 over 1 minus cos theta plus 1 over 1 plus cos theta. And what I am going to do is I am going to create a common denominator by simply multiplying those two things together. All right. So, and this is, way back in the day when you learnt how to add and subtract fractions. This is what you did. This is the process that you did. All right, so it's still the same process, just with some more complicated stuff. All right, over here there was a 1 on top, and we already had the 1 minus cos theta. So what we need to do is we need to multiply the top by the 1 plus cos theta. And with this one, we had the 1, and we already had the 1 plus cos theta, so we need to multiply by the 1 minus cos theta. All right, that's all so far pretty good. All right, so now I'm going to put all of that over one thing and expand that, and that's 1 times 1, which is 1 plus 1 times cos theta. 1 times 1 plus 1 times 1 is 1. 1 times minus cos theta is minus cos theta. So here already, I'm noticing those two are going to get rid of each other. All right. When I expand this, okay, you can recognize that it adopts. If you do, you can shortcut yourself. But if not, you can expand. So 1 times 1 is 1. 1 times cos theta is plus cos theta. Minus cos theta is times 1 is minus cos theta. Already noticed there, minus times a plus is a minus. Cos times cos is cos squared. And so what have I got? I've got 2 on the top, and on the bottom I've got 1 minus cos squared theta. All right. Now what do I do? What do I do? What do I do? Well, remember the Pythagorean. There it is there. Now if I take cos theta, squared theta, from both sides, I'll have sine squared theta equals 1 minus cos squared theta, which is what we've got there. So that's 2 over sine squared theta. Now, that's on the bottom now. And if that's on the bottom, that's our reciprocal. And the reciprocal of sine is cosec, so it's 2 cosec squared theta. And when we come back here, that is equal to our left-hand side. Not left-hand side. That is equal to our right-hand side. We started with our left-hand side. And so that's a mathematical proof. Right? So we just worked with one side, said left-hand side equals, we work with that, and we get down and we go, hey, that's equal to the right-hand side. Proven. Proven. So how do we do that? All right, so a couple of ways of doing it. One way is you can go QED. QED. So again, that's a mathematical thing that says that I've now shown what I got to show. It's Latin. Quod erat demonstratum. In English, what was to be shown. All right, so we need to prove that. We need to show that that was equal to that, and we should have shown that. Sometimes, one that I saw years and years ago, that I was told when I was at school, but I haven't really ever seen it, was you put a line and do that. So I don't know whether that's a real one or whether my teacher just made that one up. All right, so let's get rid of that. All right, so QED, there it is, QED, Latin, quod erat demonstratum, and English, what was to be shown. All right, so, I mean, that's technical things, so mathematical proof, technically, how we set it all out. All right, so that's that with that particular reciprocal circular functions, and also the Pythagorean, and using those things to find angles and things like that, but also to do some proofs. All right, so if you need anything clarified, make sure you get assistance to get it clarified, and of course, as always, have fun.